Hello my dear learners, I am Dr. Pawan Kumar Shukla and I am delivering my second lecture on the subject electromagnetic field theory and antenna. Actually, in my last lecture, I have discussed the introductory part of this subject in terms of vector analysis. As I have described that vector algebra, vector analysis, all the study about the vectors is a basic backbone of this subject. Whatever the parameters we will discuss in this subject, they will be in the form of vectors. So, the complete analysis and the complete knowledge of vector analysis is very much required in this subject. In the introductory part of vector algebra, vector analysis, I have discussed what are the vectors, how these vectors are represented and what are the different calculations done with the vectors. Today, I will proceed the same thing, the vector algebra, and the topic of this lecture is vector analysis, means vector algebra part 2. So, I am starting the subject in the form of this vector magnitude. Vector magnitude, as you know that vector is a combination of magnitude and direction both. In a vector, how can we calculate the magnitude part only? This slide represents the fact of magnitude for a vector quantity. If a vector is represented in n number of dimensions, then the magnitude of that vector can be calculated with the standard Euclidean distance metric in the form of this V, means this vector quantity V and this vector quantity V and its magnitude can be represented in the form of mod V, which is equal to under root all the magnitudes in the form of V1, V2, V3, V4 and up to n. N means n is the number of dimensions in which that vector V is being represented. For example, this example is taken for the 3-dimensional vector. If a vector is described in terms of 3 dimensions, then this vector's magnitude can be given in terms of like this, means 1, 3, 1 are the 3 components of that vector in those 3 dimensions and the magnitude can be given in terms of under root 1 square plus 3 square plus 1 square, which is equal to under root 11. Actually, vectors of length unit 1 means when the magnitude of that vector is equal to 1 only, then these vectors can be defined in terms of normal vectors. What is the need of these normal vectors? When we wish to describe the direction, we generally use the normalized vectors, and these normalized vectors can be represented in terms of this formula. As you can see that V dash is equal to V upon mod V. It means 1 upon under root in the same way in which we have represented the magnitude of the vector of dimension n, and this formula, this representation of the normalized vector can be given in terms of the unit length 1. Now, the next very important thing is the vector addition and vector subtraction. How does this particular phenomena occurs? Vector addition, here in this diagram we can see that vector addition can be done in 2 ways. First one is the parallelogram rule and the second one is the head to tail rule, means these 2 rules can be used to describe the phenomena of vector addition. In the first diagram, when we describe the parallelogram rule, what it says that if there are two vectors A and B, and with the help of a parallelogram diagram, we draw the figure and the diagonal of this parallelogram represents the addition of these two vectors A and B. In the other form of vector addition, we use the head to tail rule, in which the head of the second vector is joined with the tail of the other vector, and when we join these together in the terms of head to tail, then this vector C represents the addition of vector A and B. The mathematical notations of this vector addition and vector subtraction. Vector subtractions can be given in the form of vector addition itself, because when we add a vector to the another vector, then we can take the another vector in the form of opposite direction, and when we add these two vectors, then the result will be the vector subtraction. You can see here the mathematical notations are given here. First one, here is the mathematical notations of the vector addition, and this vector addition can be given as when any vector A is A into A, means this A represent the unit vector in the direction of A vector, and in the 3 dimensions it can be shown in the form of x a x plus y a y plus z a z, where these x, y, z denotes the directions, denotes the unit vectors, denotes the particular direction of the components a x, a y and a z. In the same way, B is represented B into B, and this is x b x plus y b y plus z b z, and the addition of these two vectors is given in terms of C, where this C vector is given as C into C, and this is given as A plus B, where the unit vectors are taken outside and A x plus B x. In the same way, where the addition and subtraction both can be done in the form of this mathematical notation. Okay. Next is, here I am going to describe this phenomena of vector addition in a better understanding way. Like this, these are the two axes, x and y axis, and when we take a vector u and v, then this particular phenomena is given in the form of parallelogram rule. This figure is drawn only to make you understand the script of the vector addition very easily. So, you can understand the thing, this is the u, this is v, and this is the addition of u and v in the form of u plus v, and this vector denotes the u plus v. If we take the example and elaborate this phenomena of vector addition, we can see that the addition of vectors follows the parallelogram law in 2-dimensional and the parallelopiped law in the higher dimension. You can see the difference in these two figures. This figure denotes the parallelogram rule, in which the two vectors are described only in x and y axis, in 2 dimensions only, but here the vectors are described in terms of 3 dimensions x, y and z, and when these vectors are described in 3 dimensions, then the addition of these vectors undergo with the law of parallelopiped. Means parallelopiped is also a 3-dimensional figure, and here the u plus v plus w can be described the diagonal of a parallelopipe. It means in 2 dimensions, here the addition of 2 vectors is described in terms of the diagonal of a parallelogram, but in the 3-dimensional figure the addition of 2 vectors can be described in addition of 3 vectors can be described in terms of the diagonal of the parallelopipe. Okay. This is the vector subtraction in the same way, where v and u are added together in the form of opposite direction. Okay. Now, we come to the next phenomena of vector multiplication, which will be most widely used in the subject electromagnetic field theory and antenna, because multiplication of vector is a very common therapy which is used for the signals, for the waves, for the notation of the different parameters which are frequently used in the subject EMFT and antenna. So, I will describe this vector multiplication in 3 parts, very simple way. First one is the simple product, means a scalar quantity is multiplied with a vector quantity. This is called the simple product, where a scalar quantity is multiplied with the vector quantity. It is given in terms of this, where B is the product of a vector quantity A and the scalar quantity K, and this product is given AKA, means this small a is the unit vector which defines the direction of this vector A, and it can be given in terms of x, y and z like this. This is the simplest form of the vector multiplication. The second term is scalar or dot product. In this scalar or dot product, there are 2 vectors which are multiplied together, but this is the form of dot product, means A and B are multiplied with a dot only, and this is also called the scalar multiplication, and this scalar multiplication gives the resultant in the form of AB cos theta, where theta is the angle between A vector and B vector, and this whole quantity AB cos theta is a scalar quantity. Means the result, means if we describe the multiplication of vector A and B in terms of C, then the resultant C will be the scalar quantity. Remember this. It means here this A and B, you can see here this A and B both are the magnitudes of the vectors A and B only. There is no direction. It means this cos theta is also a scalar quantity, and it gives the value, the magnitude of the cos theta term only. Okay. The next is scalar or cross product. When we describe the multiplication of 2 vectors in the vector form, then this is given in terms of A cross B, and this A cross B is given as unit vector n AB sin theta. In the same way, theta is the angle between A and B. Here this vector n, unit vector n, describes the direction of this resultant, means the multiplication of the cross product of these two vectors A and B, and it is given in the form of this. It means the multiplication of two vectors in the form of vector product provides a vector quantity, and the magnitude of this vector quantity is represented in terms of a b sin theta, and the direction of this is given in terms of this unit vector n. What will be the direction of this unit vector n? It is discussed in the next slides. Now, the description is given here. The first one, what is the simple product, and this simple product is described in terms of this diagram. Very easily you can understand the multiplication of a scalar quantity to the vector quantity. What happens? Actually, each vector has an associated length. Obviously, the magnitude of the vector represents its length. Here in this diagram, if we multiply a unit vector with a scalar quantity 2, it means the direction will remain same, but the length of that vector will be doubled. Here this is represented. If the vector v is multiplied by 2, then the resultant will be 2v, means direction will remain same. It means the scalar factor or multiplier will be representing in the same direction of that vector. Either it will be in the direction of x, either it will be direction of y, or in the direction of z. This whole figure describes the phenomena of a simple product of a scalar quantity to the vector quantity. Okay. Next, we come to the dot product or scalar product of two vectors. In its most generalized form, we can represent this dot product or scalar product like this. Means if there are two vectors u and v, and these two vectors are given in terms of ui vi, means these vectors can have the multiple dimensions, and these multiple dimensions may be of 2, 3, 4, 5, 6 up to n number of dimensions. Then these can be represented in terms of I is equal to 1 to n, and this is the sigma which represents the summation of all the terms. It means the summation of u1 v1, the summation of u2 v2, the summation of u3 v3, and so on. In number of dimensions, these two vectors are described. The number of I equal to 1 to n is defined in terms of u and vi. Okay. So, this is the generalized product of the multiplication of the two vectors, but here we have taken only 3 dimensional vectors u and v, where u dot v can also be given in terms of u transpose v, where u transpose is represented as u1 u2 u3 in the row form, and v is represented as v1 v2 v3 in the column form. So, the multiplication of this u dot v is given as u1 v1 plus u2 v2 plus u3 v3. It means the result is in scalar form only. There is no direction, and when we describe it in terms of this u dot v, then it is represented as u v cos theta simply, where theta is the angle between u and v. Next, when a vector is multiplied by itself, then what happened? When a vector is multiplied by itself, it means the magnitude of this can be given as u1 square plus u2 square plus u3 square, and this is the magnitude only mod u square, because the vector has 0 angle with itself, then the product can be given as u into cos 0. It means cos 0 is equal to 1. Then the magnitude of vector u, the magnitude of vector u, both are multiplied and it comes as u square only. This is a very important thing which will be used very frequently in the next lectures. What it says? It says that we can redefine the magnitude in terms of the dot product operator, and it will be used in the terms of when we describe the unit length vectors in the different dimensions. Dot product means dot product operator is commutative and distributive in its operation. You can see it. What is the commutative property and what is the distributive property? It is given here in red color. Commutative property, what it says, that A dot B is equal to B dot A. The product is same for both the notations. Either it may be A dot B or it may be B dot A. The product will remain same because it is a scalar quantity. There is no difference of the direction. So, it is in terms of magnitude only, and the magnitude is A B cos theta. Magnitude is A, magnitude is B, and cos theta is also a scalar quantity. So, there is no any change. The distributive property says that A dot B plus C is equal to A dot B plus A dot C. Both the things will be same. Okay. So, in this describe we have also defined the dot product in its more interesting manner. When A dot B means the multiplication of A with the vector B, where A and B both are defined in terms of 3 dimensions unit vector x, y and z, where this A is given as x a x plus y a y plus z a z, and it is multiplied by this. So, this whole phenomena is given in terms of x dot x, y dot y, z dot z is equal to 1. But if we discuss the 2 orthogonal dimensions, means when x is multiplied by its orthogonal axis y, then the angle between x and y is equal to 90 degree, and when we take the angle between x and y is equal to 90 degree, then it comes to the cos value of this angle 90 degree comes to 0. It means it is x dot y, y dot z, z dot x is equal to 0. This is the resultant in terms of cos 90 degree. Okay. So, I think you can understand the operational characteristic of this theta, and this theta angle between A and B can be described in terms of the cos of the dot product, means cos inverse A dot B upon A into B, where A into B is the dot product of 2 vectors, and here A and B are the magnitudes of the vector A and vector B. This derivation is defined in terms of dot product only. All the notations, all the mathematical analysis is done in this slide, and this slide shows the complete phenomena, the complete mathematical notation, the complete analysis of the dot product in terms of 2 vectors. You can see from the first one, A dot B is equal to, these are the different representations of the dot product of the two vectors. First one, A dot B is equal to Ax Bx plus Ay By plus Az Bz, and here we take the two vectors in the form of A is equal to Axi plus Ayj plus Azk, means I, j, k are the 3 unit vectors which describes the direction in the x axis, the direction in the y axis and the direction in the z axis. If we denote the vectors A and B in the form of I, j, k, then it can be written here. This is the complete multiplication of these two vectors A and B in terms of I, j, k, and the complete mathematics for the multiplication is given here. And when you have already taken the multiplication of two unit vectors, means I dot I is equal to 1, but I dot j is equal to 0, then we can replace the whole I dot I and I dot j in terms of 1 and 0, then the result will come as you have previously studied. Okay. So, this is the basic description and the analysis of the dot product. Here these are given and the result is given in the terms of Ax Bx plus Ay By plus Az Bz. Okay. So, this is my second lecture for the vector algebra, vector analysis, which will be dealt briefly in this subject EMFT and antenna. Thank you very much for being with us, and go to AKtU MOOCs video lectures for the different other lectures of Dr. Pawan Kumar Shukla. Thank you very much.